Assalamu alaikum. Welcome to the class, that is lecture 2 of the current week. Course code is CS430 and course title is Microprocessor Programming and Interfacing. Before starting today's lecture, whatever we have covered in the previous lecture is to be reviewed quickly. We have discussed internal architecture of 808 806 microprocessor in the previous lecture, and there were two logical parts of internal architecture. First one is called execution unit. So we have discussed the components present within execution unit. Then we will discuss the second part, bus interface unit and its components. In this lecture we are going to discuss how microprocessor generates address for memory. So there are two schemes, real mode memory addressing and protected mode memory addressing. So 8086 and 8086 microprocessors may operate only in real mode. 80286 and onward processors may be operating in real mode or protected mode. But whenever a microprocessor is operating in real mode operation, only 1 megabyte memory space may be accessed. So the first 1 megabyte of memory is called real memory or conventional memory. If 80286 or higher processors are operating in real mode, only 1 megabyte memory will be available. But if these processors are operating in protected mode, more than 1 megabyte memory may be accessed. In real mode memory addressing, to generate 20-bit physical address, segment offset scheme is used. So the formula for generating 20-bit physical address is segment address multiplied by 10h plus offset address. So physical address, segment address will be coming from any segment register, and offset address may be coming from some register or from an immediate address. So segment address defines the beginning address of 64 kilobyte of memory segment, while offset address selects any location within the 64 kilobyte memory segment or location. There is a table given in this slide showing the segment offset scheme. If you want to access code segment, then offset will be coming from IP, and formula for physical address will be CS into 10h plus IP, and the generated 20-bit physical address will be an instruction address. Then for stack segment, physical address formula will be SS into 10h plus BP or SP, and that will be generating stack address of 20-bit. BP will be used within move, add, subtract, and or instructions, while SP will be used for holding offset address when you are using push and pop instructions. Both of these registers will be generating stack address. Then for data segment, offset may be coming from BX register, SI, DI, 16-bit number or address may be mentioned directly into instruction. So you will be using these registers or direct address of 16-bit within move, add, subtract, and or instructions. And the generated 20-bit physical address formula will be DS into 10H plus whatever register or direct address is used as offset address. And that will be generating address of the data present within data segment. For accessing extra segment, DI register is used within string instructions. So formula for physical address will be ES into 10H plus DI for string instructions, and that will be generating 20-bit physical address for string data address. But you may use uh, another segment override prefix to change the default segment. That concept will be discussed later when we will be discussing the topic of instruction set. Now we have to discuss the concept of real memory. As we have discussed earlier during the topic of hardware specification of microprocessor, that address bus of both of the microprocessors 808 and 806 address bus is of 20 bit. So the minimum address generated by microprocessor may be 20 zeros. In hexadecimal that will be 00000 hex. And the maximum address generated by microprocessor may be 20 ones, and that will be in hexadecimal FFFFH, FFFFH. So that is the boundary of addresses. Within this 1 megabyte memory, there are 4 segments possible. First one is code segment, second one is data segment, and third one is stack segment, and fourth one is extra segment. So why we are going to access only 4 segments? Because microprocessors are having 4 segment registers. So as we have discussed the formula for physical address generation in the previous slide, so the starting address of code segment may be calculated by multiplying that code segment register with 10H. So that is the starting address of code segment in real memory. For getting the starting address of data segment within 1 megabyte memory, you have to multiply DS with 10H. So that will be the starting address of data segment within memory. Then we have multiplied SS with 10H to get starting address of stack segment within memory. And in the same way, we have multiplied extra segment with 10H with for getting the starting address of extra segment in memory. And the offset addresses for any of the segment may be of 16 bit. So maximum offset possible is 16 ones. In hexadecimal that will be 4 Fs, FFFFF, FFFFH. So we have added FFFFH with CS into 10H for getting the final address of code segment within memory. Then we have added FFFFH with DS into 10H to get the final address of data segment. For getting final address of stack segment, we have added FFFFH with SS into 10H. So that is the final address for stack segment within memory. And for the final address for extra segment, we have added maximum offset FFFFH with ES into 10H. So that is the final address of extra segment. So these are the boundaries. Code segment is shown with yellow color, and data segment is shown with green color. Stack segment is shown with brown color, and purple colored segment is extra segment. Now we have to discuss another concept of relocation. Within 1 megabyte memory, if you calculate that within 1 megabyte memory, the total number of segments possible are 16. As you divide 1 megabyte by 64k, then you will be getting which number? 16. You will be getting 16. So there are 16 segments possible within 1 megabyte memory, each of 64k kilobyte. So we are using only 4 of the segments out of 16 segments possible. So 12 segments space is available. So we may declare that more than one code segment may be present in real memory, or more than one data segment may be present in real memory. To access the second code segment, we have to change the contents of CS. For accessing the other data segments, we have to change contents of DS register. So we may access more than one data segments or code segments. If we want to, if we are having code more than 64 kilobyte or data more than 64 kilobyte. In the previous slides, we have discussed that segment offset addressing scheme is used for real mode memory addressing. We multiply 10H with segment address, and then the offset address is added to form 20-bit physical address, and that is the actual address where the code or data is residing in memory. And we have discussed earlier that real mode memory is of 1 megabyte, and in 1 megabyte memory there may be 16 portions of 64 kilobyte each without any overlap. So 16 segments are possible within real mode memory, but by using 4 segment registers at one time we may access only 4 segments. So it means that we may have more than one code segments or data segments within memory. So if you want to go to the segment other than the current one, then you have to change the contents of the segment register. For example, you are accessing a code segment and you want to access the code present in the second code segment, then you have to change the address present within code segment register, and that will relocate your segment, and you will be accessing the accessing the code present in the second segment. Same is the case for data segment. If you are having more than one data segments in memory, then for accessing data present in the second segment, you have to change the contents of the data segment register, and that will relocate your data segment, and After changing the data segment register, you will be accessing data from the second data segment. So segment offset scheme allows relocation. And if you don't want to reserve 64 kilobyte memory for any segment, then your segments may overlap. If you want only 1 megabyte memory for code, then after 1 megabyte you may place your data segment, and your data segment is of 1 megabyte, then you may have a stack segment of, for example, 100 bytes. Then you may have access segment of 200 bytes. So it is not necessary to have full 64 kilobyte segment in memory, but you may be using according to the need of your program. Now we have to discuss the concept of paragraph. As we have discussed earlier that for generation of physical address, microprocessor multiplies 10h with the segment address. So this base address for segment will be having an address whose rightmost digit will be 0 always. So if you have given a number of 20 bit which is having a non-zero result digit on the rightmost side, that will not be that cannot be a starting address of any segment. So whatever starting address of any segment, that will be having a 0 on the rightmost side, and that is because the 0 is appended by the processor, not the segment register. And because of this internally appended 0h on the rightmost side, any segment may start from a paragraph address like 0, 10, 20, 30, 40, 50. These are all paragraph addresses. So whenever a segment starts, its starting address will be a paragraph address. Now some calculations are shown in this slide. There are two examples. Example 1. Here base address is given 4F38 for a segment. Then an offset address is given 39D2, and we have to calculate the physical address. Physical address formula is physical address is equivalent to base address into 10h plus offset address. So 4F38H is multiplied by 10h. Then the offset address is added 39D2 hex. In response, we are having resultant physical address 52D52H. In example 2, offset address is given 56C4 hex, and we are having physical address B3294H. Now we have to calculate the base address or segment address. So we have adjusted the formula for calculating the base address. So physical address minus offset address divided by 10h, that will be providing us base address. So the calculated address is ABDB hex, that is the base address for the current example. Now we are moving to protected mode memory addressing. In protected mode memory addressing, data and program located beyond 1 megabyte of memory may be accessed, but the addressing scheme is changed. Now we are going to use selector descriptor scheme for accessing memory. In case of protected mode memory operation, segment register will be having three informations. First one is the selector of 13-bit, then a single bit for table indicator TI, then there will be 2 bits for RPL, requested privilege level. So the selector will be selecting a descriptor from descriptor table. By using 13-bit address, you may access 8192 descriptors. So descriptor table will be having 8192 entries. And there are two types of table, global descriptor table and local descriptor table. And these tables will be indicated by using TI bit. Which table is to be accessed? That will be indicated by using TI bit. If TI bit is 0, global descriptor table will be accessed. If TI bit is 1, local descriptor table will be accessed. Each descriptor is of 8 bytes. So we will be discussing these 8 bytes in the next slide. As there are 8192 descriptors in a descriptor table and each descriptor is of 8 bytes, so total length of a descriptor table will be 64 kilobyte in length. And format for segment register is shown here, that 13 bits are for selector, then you are having TI bit, and rightmost 2 bits are for RPL. Maximum value for RPL is 00 and minimum value for RPL is 11. In this slide, we are having descriptor format for 80286 microprocessor. For remaining of the microprocessors from 80386 onward till Pentium 4, the format for descriptor is different. So in case of 80286 microprocessor, in the first 2 bytes, you will be having limit L0 to L7, L8 to L15. So limit is of 16 bit. Then 3 bytes are for base address B0 to B7, B8 to B15, B16 to B23. So base address is of 24 bits. Then there is a single byte for access write. Access write byte will be discussed in detail in the coming slides. And last 2 bytes are 00 for 80286 microprocessor. So whatever segment is to be accessed, initial starting address for that segment will be the base address, and when base address is added with limit, that will be the final address of the access segment. That is the diagram for showing how a segment register is used to access memory within protected mode memory addressing. So you may see in the diagram figure 2-9 DS is having 0008. So if you convert data segment register into binary, pattern will be 0000000000001000. So then you may extract selector from there. So selector will be 00000000000001 and TI bit is 0, that is showing that you are going to access global descriptor table. RPL is 00, so RPL is at maximum value. Now from descriptor you may see that base is 100000 and limit is 00FF and access byte is 92 and last two bytes are 00 for this descriptor one. From this information, starting address for segment data segment is 100000 hex and the final address of data segment is base plus limit, that is 1000FF hex. We have discussed earlier the descriptor format for 80286 processor. In this slide, we are going to discuss descriptor format for 80386 to Pentium 4 processor. Here you may see that in the initial 2 bytes there is limit L0 to L7, then L8 to L15. And in the second last byte of this descriptor, in the lower nibble you are having A16 to A19. So there is a limit of 20 bit. Then there are 4 bytes for base address, B0 to B7, B8 to B15, B16 to B23. And the last byte is having B24 to B31. So base address is of 32 bit. And there is a single byte for access site. And in the second last byte you are having bit G, D and AV. So for calculating the initial address you are having base address, and for calculation of the final address formula will be base plus limit. So in this slide we have to discuss G, D and AV bits. G bit is called granularity bit. If in any descriptor G bit is found 0, then for finding the final address of the segment accessed, limit will be added as it is into the segment address or base address. But if G bit is 1, then limit will be multiplied by 4k before adding into the base address for finding the final address of the segment accessed. So limit will become limit FFF. As you have seen in the previous slide that limit is of 20 bit. By adding 3 F's on the rightmost side, limit will become of 32 bit. So the maximum size of a segment will be 4 gigabyte in case of 80386 to Pentium 4 processor. Now D bit If d bit is 0, processor will be executing 16-bit instructions and 16-bit offset addresses will be generated during the execution of program. So d bit is for backward compatibility, and if g bit is having 1, then 32-bit instructions will be executed by microprocessor. And the last bit is AV bit. AV bit is declaring that uh, the segment for which this descriptor is defined is available or not available. If the segment is occupied, then this bit will be 0, AV bit will be 0, or if segment is free to be used, then AV bit will be having 1. Now we are going to discuss accessite byte found within the descriptor in protected mode memory addressing. The accessite byte controls access to the protected mode segment. This byte describes how the segment functions in the system. This is an 8-bit pattern. V starts with the MSB. So P bit is there in the MSB. If P bit is having 1, that means in this descriptor you are having valid base and limit values. And if otherwise, if P bit is 0, then whatever values of base and limit you are having from this descriptor are not valid values. Or otherwise you may say that if P bit is having 1, then whatever values you are getting from this descriptor for base and limit are valid, and the segment is defined and present on the disk, in memory. Or otherwise, if P bit is 0, then the values you are getting from this descriptor for base and limit are not valid values, and this segment you are going to access is not present on the disk. Then you are having DPL. There are 2 bits for DPL, descriptor privileged level. We have discussed earlier RPL. When we discussed selector and table indicator, there were 2 bits for requested privilege level. So this descriptor privilege level is matched with RPL, and whenever you are accessing code segment, then a condition is checked, RPL greater than or equal to DPL. So maximum value for DPL is 0 0 and minimum value for DPL is 1 1. Here we have to discuss only code and data segment descriptors. So next bit is S bit. S bit will be having logic 1 if we are going to access code or data segment, or otherwise if you are having 0 at S bit, then that means this descriptor is a system descriptor, and remaining 4 bits of accessite byte will be having some system function code. So the scope of our discussion for this slide is to discuss the code or data segment descriptor. We are not going to discuss the system descriptor here, but you may keep in your mind that there are to the power 4, that means 16 different system descriptors may be possible. So, but we are not going into the detail of system descriptor. Now we are going to discuss data segment descriptor, then code segment descriptor. So you may found here in this slide that the font color is changed to orange color and light blue color. Orange color is used for discussing data segment descriptor, and light blue color is used for discussing code segment descriptor. So if e bit is having logic 0, that means descriptor describes the base and limit for data segment. So next bit ed slash c will be treated as ed, and w slash r bit will be treated as w bit. So data segment may be of two types, data segment or stack segment. So if you are going to access data segment, ed bit will be 0. In case of stack segment, ed bit will be having logic 1. Whenever you are going to store data within data segment, offset addresses increase. So you may say that segment expands upward. In case of stack segment, whenever you store data into stack, then offset addresses decrease. So segment expands downward in case of stack segment. So ed is 0 for data segment, ed is 1 for stack segment. Now w bit, you may protect your data by placing w bit equal to 0. So if you have placed w bit equal to 0, data may not be written into the segment by the user. Or if you have placed w equal to 1, data may be written into the data segment or stack segment, whatever you have mentioned. Now we are going to discuss code segment. A bit will be 1 for code segment, and code segment is discussed within this slide by using light blue color font. So C bit will be showing that whether you want to check the condition RPL greater than or equal to DPL or not. If you want to check this condition before giving access to the code, then C bit will be 1, or otherwise if you want to ignore this condition, then C bit will be 0. Then R bit is for uh, is to protect the code from reading. So R is 0, then code may not be read. If R is equal to 1, code may be read from the code segment. Then the last bit is A bit. A bit is uh, used by operating system to keep record of the currently accessed or recently accessed segments. Whenever operating system accesses some segment, it places 1 at A to show that this segment has recently been accessed. Or otherwise, if you are having 0 at A, that means this segment hasn't been recently accessed. So that is the last bit for exercise byte.